Okay, welcome back everyone to another installment of Geography 270. So just a little bit of housekeeping before we get into the lecture. We haven't had a quiz in a while, so do take note that quiz 4 will open up today. You guys again will have a week to complete it. All right, so the theme of the next lab on this Tuesday is correlation and regression, an important topic in statistics, especially spatial statistics. So what are they, right? So last time we looked at ANOVA and parametric version of the Kruskal-Wallis non-parametric test for telling you whether there is one group that's different when you have 3 or more samples. And then we did a little bit about an overview about how to go about choosing a correct statistical test. So now we're going to finish off with looking at correlation and regression. Two topics that are similar but are different. So keep in mind that correlation and regression are not the same. So correlation basically measures the association between two variables, right? And it can quantify that association using a stat called the R stat, and it can quantify it going from -1 to +1. Regression is different, right? It's different in that regression analysis is used to try to determine how much of a dependent variable can be explained by another variable, the independent variable. So you're trying to predict one variable from another one, where in correlation, there is no prediction, okay? But keep in mind that neither correlation nor regression explain causality. Regression can show you some potential factors that may be causing one variable to behave one way, but neither correlation nor regression explicitly imply causality. So we've done a little bit of scatter plots in the lab, right? So scatter plots are a good way to visualize the relationship between two variables, X versus Y, independent versus dependent variables, right? So you can use a X, Y, or scatter plot to see the relationship between two variables, whether it's straight, whether it's curvilinear, exponential, logarithmic, polynomial, right? And you can also use a scatter plot to see where you're going to have potential errors in your data, where the points do not line up along a straight line. So, right, we use correlation to basically look at the association between two continuous variables, whether that be, right, looking at whether tree height is related to soil moisture, the age and how many years you've been in school, a person's age versus their weight, temperature, mosquito density, right? We can plot all these up against each other. And there's 3 major ways that we can describe the goodness of our correlation, right? Or the nature of our correlation, I should say. The direction, whether it be positive correlation or negative correlation, how strong or how good the association or correlation is, and then also whether it's significant or not, which we can look at the p-value to determine whether a correlation is statistically significant or not. So here's some scatter plots of in the top left corner there, showing a strong positive correlation where we see our points basically lining up along a line. It's a positive correlation as it's pointing up. So as those points get further and further from a line, right, the correlation gets weaker. So there we have a weak positive correlation. A strong negative correlation, we see where the points are going downwards, right? So as one variable goes up, the other variable goes down. And then as those points get further and further away from drawing a straight line, that negative correlation gets weaker. Right? So we can have positive correlation, negative correlation, and then we can have no correlation, which is basically our null hypothesis. Our null hypothesis in correlation is that there's no association between two variables. It's only when we reject that null hypothesis that we're going to say we're going to have correlation either in a positive or negative direction. So how do we quantify how good our correlation or how strong our correlation is between two variables? Well, for this, we're going to be using the stat of R, the correlation coefficient, okay? So R varies between -1 and +1, okay? So no correlation, if you have a no correlation between two variables, you're going to have a R, or a correlation coefficient, equal to 0. Where you have a weak correlation between two variables, you're going to have a R equal to plus or minus 0.1, 0.2, somewhere in there. It's not until you start to get into R values of plus or minus 0.5, right, that you can consider that the correlation between the two variables is relatively strong. Then that formula at the bottom there is showing how you can compute the correlation coefficient R between two variables X and Y. Don't worry about the formula, but that formula relies on something called the sum of squares, which is essentially a stat technique used to analyze and quantify the dispersion of the data points. So the correlation coefficient, the most commonly calculated or used correlation coefficient is the Pearson's product moment correlation. So I'll just be calling it the Pearson's correlation coefficient, or Pearson's R from now on. It's the most commonly one, and it's the parametric version. So if your data is parametric, right, you can use the Pearson's R to describe and quantify the correlation between the two variables. Right, so again, the Pearson's correlation relies on the sum of squares, right? So basically you're taking the sum of squares between your X variables, your Y variables, and between the X and the Y, and you calculate the R based on that. Again, don't worry about the formula, but just that's the way it is calculated. Luckily for us, there's simple ways to do it. If you're going to use it in Excel, you can simply use the expression Pearson, right? Where you Pearson and then you put your two arrays of data, your X and your Y, your A column versus your B column, and that'll give you your correlation coefficient. So you can either use the Pearson function. In Excel 2 can also use the Correl function, right? It'll give you the same result. So you can see in this example here, I'm correlating median house value versus median income. It gives me a Pearson correlation of 0.85. So a relatively strong correlation, as you can see in the scatter plot on the right. Right, so when you're looking at your scatter plot, right, that gives you an idea of the strength or the value of your Pearson R, right? So on the top here, you can see we go from a perfect positive correlation on the left, a perfect negative correlation on the right, so an R of -1 on the right. And then as you work towards the middle, we see that our correlations get weaker and weaker. The bottom or in the middle here, all of those lines, when the points line up exactly along a line like that, we have a correlation coefficient equal to 1. And then at the bottom here, all of those have correlation coefficients of 0. There is no correlation or association between the variables if we have scatter plots that have some representation like this. So generally, right, we can go from two extremes: perfect positive correlation, R equals 1, perfect negative correlation, R equals -1, and then when we have absolutely no correlation, we're going to have an R equal to 0. Usually we're dealing with something in the middle, right? But as soon as our R values start to get either above 0.5 or less than -0.5, we're dealing with either a very strong positive correlation like we see on the left, or a very strong negative correlation like we see on the right. So again, we can look at correlation through the lens of a classical statistical hypothesis, where our null hypothesis is that there's no correlation exists between two variables. And it's only when we reject that null hypothesis that we say that there is a significant correlation between the two variables. And with correlation, we're looking at a two-tailed test. And what does that mean? Well, basically, it can be either negative correlation, having an R of, in the -0.5, say, or a positive correlation. And how we tell whether the correlation is significant or not depends on the p-value, which we can calculate for the correlation. And the p-value is going to be determined by both the sample size, right, the Rn, and also R, our correlation coefficient. Right, so again, p is the probability of what we're seeing is due to simple chance. So with correlation, right, we can have a very strong or very high R value. It can be even close to 1 or close to -1, but it can still be insignificant if we're dealing with very small sample sizes. And I'll be showing you an example of that at the end of this video. So you can think of correlation as kind of like a boxer's punch, right? The directionality, whether you have a positive or negative R value, the value of that R is going to tell you the strength of that punch. And then your P value is going to tell you whether that correlation that you are seeing is due to chance or not. Right, so we can have a simple correlation, right? This scatter plot, right? Poverty rate along the x-axis versus crime rate per 100,000. Here we have an R equal to 0.438. We'll get into what R squared is later on, but right now we're looking at R, the correlation coefficient, right? So a moderate positive correlation between these two variables. So there's our R values, 0.438 in the table there. Now, because we have a relatively high sample size, we have 51 points. When we run the stats, we get a very small p-value, telling us that this correlation that we're looking at is very unlikely due to chance, right? There's only a 0.001 chance, right? That what we're seeing is due to chance. So much lower than, say, an alpha value of 0.05. So in this case, we're dealing with, even though we only have a correlation coefficient or an R of 0.438, because we have a relatively high sample size, it's a significant result, meaning that we would reject the null hypothesis that there's no correlation, and we'd accept the alternative hypothesis, in this case, that we have a significant positive correlation between those two variables. But always keep in mind, again, correlation does not mean that one variable is causing the other one. With correlation, oftentimes we can be tricked in that we're looking at, say, two variables that appear to be positively correlated, but there's no cause and effect between them, right? So we call these spurious correlations. So for example, right, we can have a very high positive correlation between, say, ice cream sales and shark attacks. One is not causing the other, right? But they're both due. They both are related to a third variable, a confounding variable called, which in this case is higher temperature, right? People in the summer, the temperatures get warmer. People both go out and buy more ice cream, and they go to the beach more, and therefore more shark attacks. So ice cream sales and shark attacks don't have anything to do with one another, even though they're highly correlated, because they both tend to occur more when there's warmer summer temperatures. So always keep this kind of idea in the back of your mind when looking at correlations, right? So just because you have two variables which are very strongly correlated does not mean that one is causing another. Again, we call this spurious correlation, right? So here's a couple goofy ones, right? So you can see these aren't done in scatter plots, but they're done in time series. So this is looking at two variables. In this case, we're looking at from 1999 to 2009, we're looking at swimming pool drownings and Nicolas Cage films, right? Of course, they have nothing to do with one another, but they are highly correlated. Another example of a spurious correlation, right? Non-commercial space launches correlates quite well with sociology doctor PhDs awarded. Again, one is not at all causing the other one, but some third or other factor is causing them to be highly correlated, to have a high association. Always like this one, right? So this person says to this other person here, I used to think correlation implied causation. Then I took a stats class. Now I don't. And the other person says, well, it sounds like the class helped. And then the person says, well, maybe. You'd think that the stats class would help, but maybe again, it's just down to a correlation, not a causation. So in spatial stats, we're particularly interested in something called autocorrelation. So autocorrelation describes how well a variable is associated with itself. So often we're talking about two types of autocorrelation. One can be over time, and what we're interested in is over space, how a variable, whatever their variable is related to itself over a spatial framework. So if we look first at time autocorrelation, right? So you can think an example might be temperature, right? The temperature taken at a location from 1 minute to the next is going to likely be much more similar compared to if you compare the temperatures 12 hours apart. So as the closer you get in time with your measurements, the more autocorrelated those variables tend to be. And the further apart in time those variables are, tends to be less and less of a similarity between them. So again, we're interested mostly in this class in spatial autocorrelation. So we're looking at some variable along the Earth's surface, which we are going to describe by coordinates x and y, latitude and longitude, whatever. And we're looking at how a variable, which we'll call z in this case, varies or correlates with itself. Okay, so this is going to be the main topic going on for the rest of this course. So you can imagine we have three scenarios here. So you can imagine x coordinates going along the bottom, y coordinates going along the side, and then the color of each of these grid squares represents our variable z. So you can see in the left-hand picture there, we have no autocorrelation. There's no rhyme or reason in what one value of one grid is going to be compared to the one next to it. In the middle, we have positive autocorrelation, sometimes called clustering. So when we have positive autocorrelation, this means that we tend to find more similar values closer. So you can see there we have very dark values, which are clustered together, and then we have very white values, which are clustered together. And then on the opposite side, we have negative autocorrelation, where we tend to have very different values to the variable z closer. So here's an example of positive autocorrelation, right? Clustering. So this is median house prices across the United States. So you can see that we have very high values tend to be clustered together, lower values tend to be clustered together. So this would be an example again of positive autocorrelation, right? You can imagine house prices in big cities like Chicago, Los Angeles, New York, right? Are going to be much higher compared to other locations, maybe in more rural areas. So we talked so far about correlation, which we're just looking at the association between two variables. Now we're going to move into regression, in which we're looking at how one variable changes or affects another variable. So with correlation, right, we quantify the strength of correlation using the R value. With regression, we're going to use something related, but it is different. It's called the R squared, or the coefficient of determination. So just a little summary before we go on here, between marking the differences between correlation and regression, right? So we're going to use correlation when we want to look at the association between two variables. Regression we're going to want to use when we want to know how one variable, when you change one variable, how it will affect the other variable. So what's the results of a correlation, right? We get the R value, correlation coefficient, telling us whether we have a negative or inverse correlation, or a positive correlation, or no correlation. In the regression equation, right, we get a mathematical equation which basically tells us the mathematical relationship between a predictor variable and the dependent variable, x and y. So some of the assumptions, right, for correlation, right, we need good measurements, unconfounded comparisons. So we need data that is, and we're also assuming a linear relationship between the two variables. A few more assumptions with regression, right? We want to make sure that we do not have, or we do have homoscedasticity and a normality of our error distributions. We do not want our errors of a regression model to be systematic or non-random. So again, just a little sample between our little summary between the difference between correlation and linear regression, right? We're using correlation to see if there's an association, while in linear regression, we're seeing more if we can predict how one variable will change with another one, right? With correlation, we're using the correlation coefficient R. With linear regression, we're going to be using the coefficient of determination, R squared, or sometimes the R squared adjusted when we're looking at multiple regression. So in correlation, we're looking at two variables, seeing if there's an association between them. In linear regression, we might be looking at two variables as well, or three or more for multiple regression. And then how the line goes through the data, right, with correlation, right, and it's implicit. And then with linear regression, the relation is explicit. mathematically, meaning that we can define the relationship between two variables mathematically and predict one from another. And correlation does not address cause and effect. Linear regression, you can attempt to show it, but still you can have a very good linear regression model and still not having one variable causing the other one. So R squared describes how strong our regression is, coefficient of determination, and what it is essentially the ability for the regression model to allow the independent variable, the input variable, and how well it does at explaining the variance or variability of the dependent variable. Right, so if we have a scatter plot like this, we have our independent variable x along the bottom there, and we're using it to predict what the dependent variable y is going to be. And how much the x variable can predict the variance of the y variable is going to determine our R squared, our coefficient of determination. So some things that we use the regression analysis for, right? We're trying to see if some key factors that influence outcomes. So imagine that you have data on gold deposits and also how much water flow you have in an area. So you might be interested in whether you can predict gold deposits from water flow. Often when we're dealing with spatial data, we have a lot of unknown data at certain locations. So we can construct a linear regression model to try to predict unknown values throughout our study area. And then we can also use it to test hypotheses, right? So imagine that you're interested in how the variable of house value varies based on a person's income, ethnicity, or degree, university, high school, whatever. So you can go out and develop a linear regression model to see if one is a good predictor of another one. So regression analysis also allows you, especially with multiple regression, to do controls, where you basically hold all the variables constant and look at how one variable in particular affects the behavior of the dependent variable. So we're looking at two basic types of regression analysis here. When we're just looking at two variables, we're going to call it bivariate regression. And when we're looking at how multiple variables can influence a dependent variable, we're something called multiple regression, multivariate. And multiple regression is available in all stat packages, a very common technique. I'll show you a little bit in Excel at the end of this. So here's an example of bivariate regression, where we're just looking at the regression between first grade reading test scores and fifth grade science test scores for the dependent variable. So you can see here that this regression analysis explains about 31% of the fifth grade science test scores. So in terms of the regression model itself, what the regression model is trying to do is predict the value of the dependent variable, often symbolized by y. And how it's predicting it is by the input, sometimes or called the independent variable, x. And the mathematical relationship between x and y is given by the slope coefficient, which is determined by the regression model. And then we also have, we all remember our linear equation for a straight line, right? We have a y-intercept. And then in regression models, we also have the uncertainty term given by the error term. So how we draw the regression model or the line through our data is determined by what's known as the ordinary least squares model. That's how the line is drawn through our data points to give us our mathematical relationship between our independent and our dependent variables. Right? So basically the least squares method, OLS, attempts to minimize the amount of variation from each point to the straight line regression line that's drawn through them. So you can imagine the green data points right here, that's our observations. The regression line tries to minimize the total distance between all those points to where the line is. And of course, it squares all those distances, so we're dealing with all positive values. So negative values don't cancel out positive values. So we can use regression models to predict a whole bunch of things, not just continuous data, but we can use it to predict, right, binary data, right? So yes or no, we can use a regression model to predict that. We can also use it to predict a category, nominal data. We can use it also to predict rank data, ordinal data, right? Whether somebody, based on some independent factors, has less than high school, or more than high school. And then we can also use a regression model to predict the number of events that are likely to occur, like we did with the Poisson distribution. So when we set up our regression model, its basic form is going to be like this, but it's basically going to be taking on the linear mathematical model, right? Whether it might be written y equals mx plus b, right? Or y equals ax plus b. Both m and a, of course, are the same in this case. Those are our coefficients. Right? So a very simple regression model given by the straight line formula. So in the regression analysis, right, we're trying to predict the dependent variable y. That's what we're trying to model or predict. In this case, maybe we're looking at residential burglary rates. And we're trying to predict residential burglary rates based on a number of explanatory variables, independent or input variables, right? So in this case, right, our model is going to be looking at the independent variables of income, vandalism, and households to try to predict or estimate the frequency of residential burglaries. And how those x variables are related to y is going to be given by the coefficients. And then the amount of error, so those are our coefficients right there. Then the amount of error or uncertainty in our model is going to be quantified by this residual or error term. Right, so everything except the error term we can call the linear predictor. So we can have a number of independent variables being used to try to predict the dependent variables. They can all be combined to set up a regression model. Right, so again, the dependent variable, right, this is what we're trying to predict or understand, right? So when we're using regression, right, we always start with go out and collect a bunch of known y values, right? And we use these sample data of the y values to build or calibrate the regression model. And then, of course, we have our independent, sometimes called the predictor or explanatory x variables, right? These are the variables that we're going to be inputting into the regression analysis to try to predict the dependent variable. And then we have our coefficients. This defines the mathematical relationship between each of the x variables, independent variables, to the dependent variables, right? So imagine instead of residential burglary, you're trying to build a regression model of fire frequency as a function of independent variables of solar radiation, the amount of vegetation, and annual precipitation. The sign, whether it's positive or negative, of each of your coefficients tells you the nature of the relationship. So if you're trying to predict fire frequency, right, you might expect, or you probably would expect, a positive relationship between fire frequency and solar radiation, right? The more sun, things get hotter and drier, you tend to have more fires. But on the other hand, you might have a negative coefficient with fire frequency and precipitation, right? The more it rains in an area, you might expect that to decrease the amount of fire frequency. So a positive value to the coefficient indicates a positive relationship. A negative value indicates a inverse relationship. Right, so these regression coefficients, right, they tend to be stronger, right, as the value gets higher and higher or farther away from zero. When we have coefficients that are close to zero, that indicates that we have a weak association or predictive value for that value predicting what the dependent variable is going to be. And for each of these coefficients, or each of these predictor variables that we put into our regression formula, we can calculate a p-value to see if they are significant predictors or not. And how we determine the p-value for each of our X values or input values is by determining the t-stat. Remember, we looked at t-tests a few lectures back. We can calculate the t-stat by taking the coefficient divided by its own standard error. And then we can compare that t-stat to the t-distribution to get a p-value. And then if we get a p-value that's exceedingly low, say below an alpha value of 0.05, we can then reject the null hypothesis that there's no predictive value for that variable, and we can say that in fact it is a significant predictor of the dependent variable. And then in any linear mathematical relationship, we're going to have the intercept, which basically is the value that we get for the dependent variable if we set all the other independent variables, the other x's, to zeros. And the E, of course, I've already mentioned that that's the amount of uncertainty in our model. And those residuals are basically showing us how much uncertainty or how much difference we have between the observed values and the predictive values of y. So of course, we want to have a low as much as possible small residuals. The smaller the residuals are, the better our model is at predicting the dependent variable. So here we have an example here where we have a regression analysis of time, which is our x, versus y, which is our cumulative savings. So basically we're setting up a regression model that's showing us the relationship between how much time somebody's been saving, money, versus how much they've saved, which is y. And so we're using a linear regression model like the one right there. And this linear regression model gives us this particular mathematical relationship between x and y. So there's our slope, b1, right? That's what we're going to multiply our x value by. And there's our y-intercept, r, b0. So what if we wanted to predict how much somebody's going to accumulate based on this regression relationship if they save up for 9 weeks? So imagine we input right now the 400 plus the 307.5,